Hello everyone. In this video, we are going to talk about the AC circuit analysis and phasor, and we are going to see what are the definition, what are the parameters, how we can analyze the circuit uh, in AC situation, in when we have like AC signals for both voltage and current, and we are going to also go over the lab assignment 4, and we see how we can actually run the lab assignment 4 in our laboratory. Now, let's start with the basic definition of the AC. So far we only work with a DC system. In a DC system, here we have a DC magnetic field also, but the definition is that we don't have a change of polarity in our signal. That means if the voltage is positive, it remains positive through the time. Okay, so it does not cross the zero line. But for the AC analysis and AC signals, we have a signal that would change the polarity. So if you have a voltage, okay, an arbitrary voltage, the voltage would change polarity in a certain times. Okay, if the voltage changes polarity based on the Ohm law and the general laws in electrical circuit, you know that that means the direction of the current would change. For example, if here in a positive half cycle we have a certain direction of the current, here in a negative half cycle we are going to have a reverse direction of the current. Okay, now I want you to pay attention to this fact that simply variation in a signal doesn't mean that we have an AC circuit. We can have a variation of the signal, but since it doesn't cross the zero line, that means the current would not change direction. So we have a DC with some variation. We normally call this variation ripples. Okay, now if you remember from the circuit analysis, when we wanted to talk about the AC circuit, we only talked about the sinusoidal functions. Okay, but how is that? Because as I mentioned, we can have any arbitrary signals as our voltage or current as long as they would cross the zero line. So we have a positive cycle, a positive portion of the cycle and negative portion of the cycle. Okay, then we have alternating current. Okay, so why we only learned to deal with the sinusoidal, to work with the sinusoidal. The reason is the Fourier transform. Okay, the Fourier transform basically changes any arbitrary voltage, okay, to a summation of several sinusoidal signals with different frequency and different amplitude. Okay, this is one example. We have a square wave, and if we take a Fourier transform, we are going to have some a sinusoidal signal with different frequencies. You can see different frequencies here, 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 and each frequency have different amplitudes. So the summation of these variations, these alternation, would give us a square wave. A square wave at the output. Now remember, when you wanna to analyze a system, frequency is something that we cannot mess with. So for example, if you have several frequencies in your circuit, you have to analyze the circuit for each individual frequency. Okay, so we do the analysis number 1 for the first frequency, analysis number 2 for the second one, all the way to the rest. Okay, and the overall result would be the superposition of all those analysis, the result of all those analysis. Okay, so now that being said, let's go a little bit deeper and talk about the what is the phasor and what is the relation of the phasor and sine and cosine wave. Okay, when we have a sine and cosine, okay, we can represent these sine and cosine as a projection of a certain vectors that is rotating with the speed of the frequency that we have, okay, and on each individual time the projection of the value on x axis is going to be the amount of cosine that we have, and the projection of these values on the y-axis is going to be the value of the sine of that frequency that we have. Let me use another color. So for example, in these vectors, this is the value of our sine when our vector reaches this point, and this is the value of our cosine on that specific time. So this vector is rotating, okay, and is, for example, at time 1, okay. The angle here is going to be omega frequency time 1. So the sine and cosine could be described by that angle of the frequency. Okay, the representation with this vector, we call it a phasor representation. So each vector basically has an amplitude. So if we have a vector v, okay, this vector has an amplitude, okay, and a phase. Let me show it by this one. Yeah, a phase. That phase is this theta. On each time, it would have a certain phase which shows basically the direction of the vector, and an amplitude which shows the strength of this vector. Okay, so this is the definition of the phasor, okay, and the relation of the phasor with sine and cosine functions. Now, before we start to see how we can develop the phasor from sine or cosine, let's see what is actually the sinusoidal voltage. What are the characteristics of this sinusoidal function? Okay, in a sinusoidal function, we have an alternation around the zero line. Okay, each sinusoidal, based on the coefficients that it has, would reach a peak value. This peak value, we call it maximum value. Okay, so this I max, for example, here is going to be the peak value that this current would get when it has a sinusoidal variation. Okay, now there is another way to consider to represent the amplitude of a sinusoidal, okay, and it's peak to peak value. So from the positive peak to the negative peak, we have the peak to peak value. And it's easy to understand that the peak to peak value is basically 2 times of the max value. Okay, now we say that the sinusoidal has an alternation. That means it has a cycle and it will repeat itself over time. Now there is another characteristic that defines the speed, or like the length of each cycle. The speed of variation, alternation, and the length of a cycle. The time that it would took our function, the sinusoidal function, to complete one cycle, one full cycle, we call it period. Okay? And based on the definition, the frequency, which is in hertz, okay, is going to be the number of cycles per 1 second. By the definition, you can see that the frequency and time period has a reverse relation. Okay, frequency is how many times we have a full cycle in 1 second, and period is how much it would take us for one period, for one cycle, one full cycle. That means the period is 1 over f, or frequency is 1 over the period. Okay, now we always, when we talk about the radian, we always work with the omega when we talk about the sinusoidal. Okay, the omega is angular frequency. This is frequency. This one is angular frequency. And we already know that the relation is simply by transferring the frequency to the radian, we are going to have that the omega is simply 2 pi times f, because each cycle would be 2 pi radian. So angular frequency is 2 pi times regular frequency, linear frequency. Okay, now in a sinusoidal value, there is another way to, in a sinusoidal function, there is another way to represent the amplitude of the signal, which we work with that parameters pretty much always. Okay, when we want to talk about the sinusoidal, we normally work with another parameters beside the peak or peak to peak, which we call it the RMS value. RMS is short for root mean square. Okay, so basically you would have a summation of the square of the values in one period, okay, and then take an average of that, and the result would be under a square root. So root mean square, okay, and it's going to be I equal to RMS. Now there is a good characteristics when we talk about the sine and cosine, which says that RMS is normally the maximum value, maximum, not peak to peak, maximum value divided by a square root of 2. This is only happen when you have a sine or cosine function. So it's easier to calculate that. Okay? Now, the transformation from the time domain to phasor domain that we introduced, okay, is very easy. As we said, the cosine is the projection of the vector as well as the sine. Okay, cosine is the projection of the vector at x-axis, and the sine is projection of the vector at y-axis, which is the imaginary kind of like axis, and this is the real axis. Now, we can represent our vector based on amplitude and the direction. Okay, now the direction of our vector is the theta that we have at time 0, because after time 0 is just rotating through the time. Okay, so the initial direction is going to be the theta, whatever is inside the cosine at time 0. So we can represent the phase of our vector based on whatever is inside the cosine at time 0. Now the amplitude, we can consider that as a Vmax, but this is not a proper is not in the best and optimal way to calculate that. Why? Because Vmax has an alternation regarding the omega. How we can get rid of that? Same as I talked about the root mean square, because root mean square will basically eliminate the time variation. So we can accurately represent this phasor of this cosine by the voltage of RMS and the initial phase angle, which is whatever inside the cosine at time 0. Now, the reference for phasor is cosine, because this is a projection over the real axis. If you have a sine, you need to change it to the cosine. And if you change it to the cosine, it simply is Vm cosine of omega t plus phi minus 90 degree. You already know that from the algebra or like calculus or these math courses that you passed. So if you have a sine, your phasor is going to be the RMS value, initial angle, minus 90. Same goes for the current. This is for voltage. Same goes for the current. So this is how you can transfer the sinusoidal value in time domain to the phasor value, which is in a frequency domain. Okay, now when we talk about the circuit analysis, we said that we are going to deal with the passive, like generally we are going to deal with a passive component like resistance, capacitance, and the inductance. Now in DC values, at DC we said resistance remained resistance, capacitance is open circuit, and inductance is a short circuit. But what would happen in AC signal? Okay, because the capacitor and inductor has a differential integral relation between the voltage across them and the current passing through them. So if you remember, capacitor voltage was 1 over C, the integral of the current, and this is C. And the inductor voltage was L times the differential of the current passing through that. So because there is a differential integral aspect to that, when we talk about the AC, okay, now these integral and differential has some values. It's not just 0 or infinity. Okay, it has values. If it has values, that means like a resistor, it would have some effect on the circuit. Okay, that means now we need to describe these and consider these C and L in the AC analysis. But as we know, it's very hard to analyze like a complex circuit and at the same time deal with the integral and differential kind of like equations. So we are going to introduce another concept named impedance, which you probably also heard about that when you talk about the S domain and Laplace transform. Okay, and we consider the impedance as the phasor domain representation of these three components. So when we talk about the AC signal, okay, we are going to use the impedance of these components. The impedance of the resistance is going to be the same value because it doesn't have a differential integral time variation characteristics in it. The impedance of capacitor, we call it minus J over omega C. Okay? Because it has an integral relation between voltage and current. And for the inductor, we have an impedance equal to omega J omega L. Okay, because we have a differential here. Okay, now, if we have such a system, when we have a real number and imaginary number here, that means the total impedance that we have in our circuit is going to be a complex number. We call it the impedance Z, and it's going to have a real number and a complex number. Real number, as you can see, is mostly resistance. Okay, now granted, if you have some high order parallel complex network, these imaginary numbers can get multiplied by each other. That means those j would cancel each other out, or can be divided by each other. So these j cancel each other out, and you would have another real value created by C and L. But in our course, because we have a simple circuit, we are not going to see these kind of like interaction. So in our level, the real part is normally comes from the resistance, and the imaginary part comes from the capacitor and the inductor. Now this X, we call it reactance. Okay, we call it reactance, which is the imaginary part of the impedance. Okay, now, as we mentioned, the real part of the impedance is R, and it's purely real. The imaginary part, if its inductor is j omega L, and if its capacitor is 1 over j omega C. Okay, so this is how we can transfer the capacitor and inductor, which are integral differential components, into the phasor domain or frequency domain, and have only an imaginary number as a coefficients, which based on the look of it, you can see that it would it would simplify our analysis between V and I to simple Ohm law, when V is simply Z times I. Now Z now is complex number. Now, there is an aspect of phase shift when we talk about these three components. We said R is simply a constant real number. If it's a real number, okay, and it's constant, that means the relation between V and I is simple linear relationship. So there is no phase shift. This R is simple real number, is not complex. That means it doesn't have any direction. It's just the real constant number multiplying by I and become V. So when you have only R, the current and the voltage are simply has a linear connection. So there is no change in a direction of the voltage and current when we deal with a resistor. Because of that, we say resistor creates an in-phase relation between the current and voltage. There is no difference. Both of them, voltage and current, cross the zero line at the same time and have a peak value at the same time. Now, but when we talk about the inductor, because of that differential value, which we say, like for example, if the current is a sine function, okay, that means the voltage is gonna be a certain coefficient times cosine function. So we are changing the function, and you already know that the sine and cosine has 90-degree phase shift with each other. Okay, so that means when we talk about the inductor would actually change the direction between the current and voltage. So if you have a current with the direction of 0, like exactly at the x-axis, the voltage from sine become cosine, which means we have a 90-degree phase shift. Okay, now if we have a 90-degree phase shift between the current and voltage, meaning the current phase plus 90 become the voltage phase, that means we have a phase shift between the voltage and current. Now, is it the phase shift like a positive phase shift or negative phase shift? Or another way, is the current leads the voltage or lags the voltage? How we can find that? You can consider this graph, this phasor graph. You are gonna watch these x-axis. These are rotating vectors. So if you see, first voltage would cross the x-axis, and after the voltage, 90 degree after the voltage, now current would pass that. So current lags the voltage. So we have a lagging current. From the time domain, you can see that voltage crosses the zero line at A, and 90-degree later, current would zero line at B. So current lags the voltage. You can also see from the peak. Voltage get to the peak before the current. So current lags the voltage. Now, in capacitor, with the same analogy, because it has an integral, we know that we are going to have, again, 90-degree phase shift, but in the opposite way. So whatever current we have, the voltage would fall behind. Okay? So what's going to happen? Now we have a leading current. If you watch here, first current would pass the x-axis and then the voltage would pass the x-axis. So current leads the voltage. With the same analogy, you can see how the time domain also works. Okay, now let's talk about the assignment that we have. In the assignment, we have an RC circuit and we want to calculate the impedance, the phase of the impedance, the voltage across the resistor, the voltage across the capacitor, and the phase shift between the voltage of the resistor and the source and voltage of the capacitor and the source. Okay, now how we can calculate the impedance? It's simply impedance is R plus JX. R is the resistance, we know, so it directly goes here. And the reactance, the X, we know that the X of C is minus J over omega C. So we have the C, we calculate that, it goes to the X. Now we have a complex number. The theta, the phi, which is the phase angle of this Z, is simply going to be the tangent inverse of the ratio between X and R. You can, if you have a question where this came from, remember the relation between the vector and sine and cosine. This is sine, this is cosine. This part is R and this part is X. So this theta, the tangent of this theta is gonna be X over R. So the theta is gonna be the tangent inverse of X over R. Now, this way you can calculate the phi and the complex value of Z. Sometimes you want the amplitude of Z, which is simply the amplitude of this complex number, which is the square root of the real part square plus imaginary part square. Now you can have the amplitude of the Z. Now, how you can find the value of the voltage for the resistance and capacitance and the value of the current passing through through those systems. Now, for calculation, if you have the Z, okay, you can simply say that, okay, I have a source and an impedance, which I already calculated the values. Now it's simply Ohm law. It's a simple Ohm law. So the current passing through here is simply the voltage divided by the impedance. Okay, and you have the current, which is going to be a complex number again. Okay, now the voltage across the resistor is going to be resistor times that current. This is the VR. And the voltage across the capacitor is going to be X of C times that current. Okay? There is a J also here. Times that current. So you can basically calculate these two with each other from the R and current that you find. Now, You know how the complex number and a phasor works. If you have a phasor A that is multiplied by a phasor B, okay, the amplitude is gonna be AB, simple multiplication, and the phase are gonna be added together. Okay, that way you can find the phase difference between voltage R and voltage source, and from this relation, and voltage C and voltage source. Okay, now let's talk about how we can use the oscilloscope to actually measure those. Now, when you have your oscilloscope, okay, you are gonna measure. You're gonna connect one channel to the source, okay, one channel across the resistor, and another one across the capacitor. Okay, now you can do this 3-channel, or do first do the VR and then do the VC. It's same kind of like scenario. When you have the V of R, the voltage across the resistor, since you have the value of the resistor, that means you can calculate the current. So then you have the amplitude of your current. We are going to consider the voltage of the source as reference. So the voltage of the source would have 0-degree phase shift. Okay? Now, whatever voltage you get across the current would determine the phase of your current. Now, we don't need that, so let's move on for the difference between the phase of the resistor voltage and source and capacitor voltage and source. Now, to do that, you already have the measurement, the sinusoidal measurement of both source and, for example, voltage of the capacitor. Now, this is gonna be, for example, what you are gonna see in the oscilloscope. So one of them are gonna be source, another one is gonna be, for example, capacitor. You don't have the access to the phase difference, but your function is in time difference. And we know that the phase difference in phasor basically translate to the time difference in a time domain. So you can measure the difference of the time, the shift of the time between peak to peak, or 0 to 0, 0 to 0 and peak, they are going to be the same, and have your delta t, the time shift between the values. Now, you need to translate this delta t to the phase change. The formula for that is simply delta t over the one period, which gives you like a percentage wise or per unit wise of the phase shift for in respect to one full cycle. And we already know that the full cycle is 360 degree. So whatever ratio of the time shift you have is going to be times that 360 is going to be the phase shift that you are going to have between the two values. Okay, so this is how you can calculate the phase shift between the voltages in your circuit. Now, same goes for the RL circuit. It's not difference. The only difference is that now X of L is J omega L. That's the only difference. The rest goes the same. You calculate the time here. You have the phase difference. You can calculate the value of the Z, the amplitude of the Z based on the values of the X of L and R. You can calculate the phase of the impedance based on the tangent inverse of the ratio of the X and R. You can use the KVL and Ohm law to calculate the current. and calculate the amplitude of the Z. So this is how you can basically run an AC analysis and solve our lab assignment. Thank you very much and have a great